Now we have set up our problem as two differential equations, one of which, for the center of mass motion itself of the entire hydrogen atom, was so simple we've already solved it. Our next task will be to solve the second equation, the equation for the relative position of the electron and the proton. Before doing that formally, we can perform a very rough solution, just to get the scale of the problem and to set up some more convenient units.
So we're going to presume that the hydrogen atom we get in the end will have some characteristic size. And we'll call that characteristic size the Bohr radius, and we'll give it the label A with a subscript O on it, A naught. And we expect, therefore, that the kind of magnitude of the potential energy we'll be talking about will be the one that corresponds to the electron and the proton being separated by approximately this amount of distance, whatever it is. And we could strictly call that the expectation value of our potential energy, but we're only evaluating this approximately. And so that, therefore, would be something like minus e squared over 4 pi epsilon naught times this separation distance here, the Bohr radius. So that's roughly the scale that the potential energy will be in this problem, we think. For the kinetic energy, we're going to look at what happens when we have some reasonably smooth wave function of characteristic size of order A naught, Bohr radius. So I've just sketched some relatively smooth function here, and the value of the function in the middle, I've called it psi of 0. And I've given the function a rough size of about A naught in each direction out here. Now, I'm only doing this also in one dimension, so this is not in any sense correct, but it can give us a rough answer here. The second spatial derivative, just considering this one dimension here, will be something that is really the difference in the slope of this line minus the slope of this line. That's roughly how much the first derivative is changing from one side to the other of this function, and divided by the distance over which that change takes place. Now, we could choose various different definitions for these that would give us slightly different answers, but it doesn't matter here. We're just trying to get a very rough answer. So the approximate scale of the second derivative is something like this slope minus that slope divided by this distance here. And that's going to give us approximately minus psi naught over A naught squared. Now, this is only meant to be a very rough estimate here. It's not exact in any sense, but we're trying to get the general scale of what this second derivative will look like. And we're only expecting to get it right within some moderate factor. We could have made definitions differently, or we could have tried to do this more formally in 3 dimensions, and we would have got slightly different answers. But we're just looking for the general scale here. Now, we remember that for some mass mu, the kinetic energy operator, of course, is h bar squared over 2 mu times del squared, and we've just figured out a very rough estimate for del squared, and that would therefore suggest to us that the rough scale of the kinetic energy in here would therefore be about h bar squared over 2 mu times A naught squared. Remember, our second derivative that we worked out for a relatively smooth function is really a negative number, and that's why the negatives cancel here. Now, we take an approach known as a sort of variational approach. This is an approach that we can justify a bit more rigorously later on. And in an approach like that, we adjust a parameter such as A naught here to try to get the lowest value of the total energy. And as I said, such variational approaches can be justified rigorously in more complete versions of a theory as approximations for getting to the lowest energy. So we're going to add the kinetic and potential energies together, and we're going to adjust this distance here to try to minimize the total energy of the system in the hope that that will give us some reasonable estimate for the energy that the system is going to choose. So with our very simple model here, the total energy, the sum of the kinetic and potential energies, is here's our kinetic and here's our potential energy, a negative number. And the total energy is a balance between the potential energy, which is made lower, that is more negative, by choosing a smaller Bohr radius, and the kinetic energy, which would get larger if we make the Bohr radius smaller. So in this expression, there's some optimum. If we squeezed it too much, we'd put the energy from the kinetic term up, and if we don't squeeze it enough, the potential energy won't be low enough. So a balance between these two. And for this simple model then, with our total energy written like this, differentiation and trying to find the minimum in that basis, we'll find a choice of A0 that minimizes the energy overall. And that will be this choice here. So simple differentiation to find the minimum of this as we adjust A0 would give us a value of A0 of this form here. And that form corresponds to about half an angstrom, or about 5 times 10 to the minus 11 meters. And that we will call the Bohr radius. In fact, I have chosen my various arbitrary constants throughout this argument, of course, to get the sort of right answers at the end. But anyway, this A0 here is the rigorous definition that we're going to find later on for what we call the Bohr radius of the hydrogen atom. So we can see, therefore, on the basis of this very rough argument, that the hydrogen atom is approximately 1 angstrom, or 0.1 nanometers in diameter. With this choice of Bohr radius we've just come up with, the corresponding total energy of the state, if we plug that back into our previous formula, would be this expression here. And we can usefully define something that we call a Rydberg energy unit. So that's just this expression here without the minus sign. This energy unit here is called the Rydberg. It's written with the characters capital R, small y, and its magnitude is approximately 13.6 electron volts. And in that case, the energy of the hydrogen atom in what we presume is its lowest state would be minus 1 Rydberg, or minus 13.6 electron volts. So, though we have produced these terms, the Bohr radius and the Rydberg, by very rough arguments, very informal ones, they will turn out to be rigorously meaningful as we go through the proper derivation of the solutions of the hydrogen atom. And from this rough argument, we could get numbers of roughly this scale as what we expect as the kinds of solutions from the hydrogen atom. And indeed, the lowest energy state of the hydrogen atom is, in fact, minus 1 Rydberg.
So now we have the equation we want to solve, a Schrödinger equation for the relative motion of the electron and the proton. And we've understood a rough estimate of the solution. The full solutions of this Schrödinger equation will be the hydrogen atom orbitals, the energy eigenstates, and the energy eigenvalues for the hydrogen atom. In the next section, we will complete the solution of the hydrogen atom.